Welcome all. Myself, Dr. Sapna, Assistant Professor from the Department of Electronics and Communication Engineering, Kalenia Kannanadi Institute of Technology, Coimbatore. In this video, let us discuss about the fundamentals of optical sources. The basic parameters we are considering in this critical parameters principle, that is how the light interaction takes place in the semiconductors, the recombination of electron hole pairs, and the efficiency and the carrier recombination. Critical parameters. When we discuss about any transmitters, it is essential that we have to transmit the data, either whatever is the type of the data, to be transmitted either in digital forms as ones and zeros. So these ones and zeros are to be either in terms of amplitude or in multiple phases or a combination of multiple amplitude and phases. So in order to consider all these factors, we have to design the optical sources. So the light emission is more important for any optical sources. So whether we can have LEDs or the lasers, which are basic light sources. In these LEDs or lasers, the fundamental parameters we have to consider or look into are the emission wavelength. What is this emission wavelength to take in? The power. Power is essential to transmit in any signals. So the power is related with the emission wavelength, how much amount of signal power is being transmitted. And the next is attenuation. Attenuation details the losses, how much amount of signal loss during your transmission. So our wavelength or the emission wavelength describes or take into account of your attenuation. And the next will be the speed. When we consider about the speed, how fast the signal can be transmitted in the system. Then comes the modulation. What is modulation? Can have any type of modulation. So the bandwidth is more essential in this. Then comes the bandwidth, the noise. Noise, either it can be in amplitude or in terms of phase. So when you consider about the amplitude, it can be basically the noise. But when you take about the phase noises, it is being described in terms of a parameter called line width. So these are the basic fundamental parameters related with the emission wavelength, that is power, attenuation, speed, modulation and the noise. The second parameter to be considered is the spectral width. So how important is spectral width is depending upon what type of the laser or the LED we are using. That is depending upon whether it is a narrow band source or whether it is a wide band source or whether we are using a tunable source. So if we are considering about a tunable source, we are all familiar with the narrow band and wide band source. But when you consider about the tunable source, it means that if there are multiple frequencies like FC1, FC2, FC3, that is the carrier frequencies, then we have to design our parameter in such a way that it can accommodate all these spectral frequencies. So the spectral width is very, very important in considering the optical sources. So we have either narrow band, wide band or multiple carrier frequency inclusion, which is in basically the tunable. Okay. The next is modulation. Modulation is concerned not only of the speed, it also concerned type of the modulation, whether it is a baseband modulation, that is direct modulation, and it can take up the amplitude modulation or the phase modulation. And the next parameter is to be considered is the angle of divergence. When you speak about the angle of divergence, it indicates how much more the signal is being spread. At one angle, the signal is being diverged, and it determines how the ability of the fiber to be coupled. That is, the signal, whatever is available, it should be narrowed down or pointed towards the fiber, which it can couple or take it directly to the fiber. So the amount of signal available from the source should be directly coupled to the fiber we are using. So the angle of divergence is very, very important parameter in considering the optical systems. The next parameter is power or the energy consumption and the efficiency. When we deal about the power, any system, basically the electrical circuit, is concerned the power. So maximum can transmit, but whenever you concern the energy consumption, maximum available power should not be, we should use only the low power consumptions. So input power should be minimum, or you can say the circuits should consume only minimum power, which affects the cost of the system. The last parameters in this is efficiency. The efficiency of the system, which determines how much amount of the signal is maximized in the system. So efficiency in terms of the power as well as the cost should be considered. The next factors to be considered is the compactness, reliability, and the cost efficiency. When you say about the compactness, almost all devices should be compact enough, and reliability, that is how much it is reliable or how much we can depend on, that relate to the security issue too. So this optical or semiconductor devices, whatever is available, there are different semiconductor devices which has got all these possible parameters, but taking into main factors compactness, reliability, and cost efficiency, we can say that LED and lasers are the most possible sources for the optical transmitters. The light sources basically are LED and the lasers. And because of the cost, efficiency, reliability, and the compactness, it can be practically deployed and commercially available optical sources for any fiber communication system. What is the basic principle behind this LED or the laser or the optical sources? This is basically what we have studied in the lower class, maybe from the 12th standard onwards. That is the light matter interactions. What are the basic parameters involved in the interaction between the matters, electrons and holes? There are three fundamental parameters included in this, that is photon absorptions, spontaneous emission, and stimulated emission. So we'll just look into all these three parameters. Before we concern with, we'll just discuss about the EK diagram. Already we have discussed about the energy band diagram. All will be knowing about what is energy band diagram. It relates with the energy and the valence band and conduction band. How much amount of energy is present between this valence band and the conduction band. Normally the holes will be present in the valence band and electrons will be present in the conduction band. So the minimum amount of energy present in the conduction band to the maximum energies in the valence band is basically the energy gap. So EK diagram is something different from that of the normal energy band diagram. Here we have to consider about the K, which indicates the momentum. We have to consider about the momentum of this system also. So here we can just see whether it balance of this moment is very essential for the transmission, or we can say recombination of electron hole pairs. So the energy band or EK diagram indicates the momentum and the energy. Momentum in the x-axis and energy in the y-axis of any valence band and conduction band. We'll just see how it is been happening in a normal semiconductor and a compound semiconductor. So that is for direct band gap semiconductors and indirect band gap semiconductors. So this shows what is a direct band gap semiconductor. We can just see that the topmost portion of the valence band and the bottommost portion of the conduction bands lie in the same line of your momentum. That is a direct band gap semiconductor. This happens normally in the gallium arsenide semiconductors. But when we take about the normal silicon, it differs. So whenever this energy gap is very normal, that is when we have this momentum to be unit, we will be able to have the emission of the photons. Otherwise, it is not possible. That you can understand from the indirect band gap semiconductor. We can just see this. For this indirect band gap semiconductors, we can just see that what is happening for the silicon. That is here, this is your gallium arsenide, your valence band and conduction band. Energy will be on the same line. But the top portion of the valence band of silicon and the bottom portion of your, or the minimum of your conduction band on silicon is differing in different positions. It is not in line with the energies. So momentum. So what is happening is that there is a space or difference between this top portion and the minimum of the conduction band. The maximum of the valence band and minimum of the conduction band electron energy will be of different positions. So the recombination is not easily done here. But in this case of gallium arsenide, we can see the recombination can be easily done. So there will be an emission of photon. But in this case, it is not so. What will happen means there will be some emission of energy. It can be a thermal energy and it can also be converted into kinetic energy. So there should be some any recombination center is essential for this indirect band gap. So in case of LEDs or your lasers, it is essential that we need a direct band gap sources or semiconductors. Now let us see what are the different three phenomena involved in the laser or the LED or the basically the sources of your light. So let us see what is happening in an absorption. So what is basically absorption? Photon absorption normally done in the photodetectors, that is the detector part, receiving part, and emissions. What you need, that is basically how this photons are emitted or the light is emitted. So there are two types. You can say the process is either spontaneous or stimulated. Let us discuss these three in detail. Now the first one, it shows the photon absorption, that is the E1 and E2 indicate the energy levels. So this is related with the valence band and E2 related with the conduction band. In the valence band, there will be some holes, free holes, and there will be free electrons in the conduction band. So you can say this is in the ground state and this is the excited state. E1 is the ground state and E2 states the excited states. So at normal condition or thermal equilibrium, you can say that you are energizing this and the presence of photon, or when you can say that some light falling on the semiconductors, photons can be absorbed to generate the electron hole pair. This is called absorption. That is, whenever light falling on the semiconductors, we know that any PN junction, that is semiconductor, will be capable of having some bandwidth. Okay, you can say that you have the band gap energies and based on that you will have some absorption of light and it indicates the electron hole pair recombination. So leaving the holes, the valence band and electrons in the conduction band. So energy is absorbed and it will be given by E2 minus E1. So the band gap energy is the difference in the valence band or the energy between the valence band and the conduction band. So the band gap energy is more important in this. The next is emissions. If already there is an electron, or can say the electrons in the lower band, that is E1, and holes in the E2, there will be at the presence of normal direct application of the current, there will be some emission of photons, that is called as the spontaneous emission. That is without any additional or excess electron transfer, there will be some carrier, without any carrier injection, without any additional support of your electrons and holes. The presence of normal electrons and holes recombine with the application of the current. That indicates the spontaneous emission. That is, it emits instantaneously without any additional carriers. This is the first principle and this generates some light sources or photons. The energy will be equal to the photon energy. The emitted light will have a photon energy and this is normally applicable in case of your light emitting diodes, LEDs. This is the principle. Spontaneous emission is the principle in light emitting diodes. And your absorption is the basic principle for your photodetectors. And the last one, the third one, it indicates the stimulated emission. What do you mean by stimulated emission? Spontaneous emission, in the normal case or in general, it is directly applied based on or the photons are emitted in its natural manner with the application of the electric supply. Yes. The stimulated emission, we additionally provide some carriers. That is, you can apply the holes towards the excess holes are injected or carrier injected either in the valence band and the conduction band. To the valence band, you can say you are including number of and the holes, and in the conduction band, you can say you are injecting additionally excess of electrons. These additional or excess carriers, whatever is being injected, that supports the emission of photons or the emission of energy, and that energy will be more in excess compared with the spontaneous emission. So more amount of energy injected or the carriers are injected, that much amount of energy will be released as photons or the light. That is stimulated emission. Thus, the basic principle behind our laser is the stimulated emission. So, we have seen the three parameters: photon absorption, photon emissions, and that is either by spontaneous manner or stimulated manner. So the spontaneous emission is basically applied for the LEDs and stimulated emission is basically applied for the lasers. This is the natural process. This is with the additional of injected carriers. So when we consider about these, we can say only the energy band or the energy consumption is not essential, but we also should maintain the momentum also to be conserved. So energy conservation and momentum conservation both plays an important role in the emission of photons. And we can say whenever you consult about these LEDs, you can say it is spontaneous emission in the sense that the emitted photons can be in random in nature. In the sense, whenever we apply the current, it emits some photons and it will be spontaneous. Spontaneous can be random also. The phases cannot be or phases need not be in phase with each other. Random recombination of electron hole pair takes place and it is incoherent. You can say the emitted photons can be incoherent. It is not coherent or in phase. So normally the light emitted from the LEDs, it can be incoherent due to the spontaneous emission. Or can say that can also be in terms of the random combinations, or further random combination indicates that it will be of the random emission of electrons and holes. Recombination takes place in a isotropic manner. That is, it is isotropic in nature, but it will take some Gaussian phase. It is random, so it takes some Gaussian phase, not as in case of stimulated emission. In stimulated emission, you can say even with a single electron hole carrier, there will be that is, you are injecting few carriers that can lead to multiple emissions. And multiple emissions leads to in phase. Whatever is being present, the emitted electrons because of this injected carriers can also be in phase with the what is emitted normally. So what is happening? That will be in phase with each other. So you will have a coherent light generation in the stimulated emission. So it will be having in phase propagation, that is coherent. The generated light will be coherent light, but in spontaneous emission it is incoherent light. This is regarding the process involved in radio electron hole recombination process, that is photon absorption, photon emission and stimulated emission. Photon absorption for the photodetectors, emission will be either spontaneous emission, which is regarded for the LEDs, and stimulated emission basically for the lasers. This is the basic principle behind the laser sources. So normally when you take about the lasing, it is the population inversion. The main process involved is population inversion, or the condition will be the population inversion. How the pumping action takes place. That is, in normal or thermal equilibrium, the stimulated emission is essentially negligible, is very low. But when there are excess density of electrons which is being excited, what is happening is optical emission is mainly because of the spontaneous. Stimulated emission will exceed the absorption only when the population of the excited state is greater than that of the greater ground state. You have your ground state and the excited state. So the population of the excited state becomes greater. In that case, we have the population inversion, which is the main principle in case of your laser. So we have seen the principle of your LEDs and the principle of the lasers. So in LED, we can say it is only the spontaneous emission, which is its normal condition. But in case of lasers, we are giving additional carriers or excess carriers makes it to be stimulated emission. So this stimulated emission and spontaneous emission are basically involved in the laser or photon generation, the light generation principle. The next topic is rate equations and the quantum efficiency. So rate equation indicates how much amount of your electrons and holes are recombined to form the amount of photons or the energy that is being emitted in the form of light. When there is no external carrier, the excess density decay exponentially. So we can say we are taking how much amount the electrons and holes recombine. So we have to see what will be the amount of recombination or the rate of recombination we can consider. So here considering the electrons and holes, we can say the energy density. Electron density say n, the recombination rate will be given by n naught into e power t by tau, where t is the time taken and tau will be the lifetime or the carrier lifetime. So how much amount of electrons will be present in that within a particular period or duration, how long the electrons will be existing within the system. So that gives the recombination rate. So the time is to be considered as well as the rate is to be considered. So we can say normally it will be given by n will be equal to n naught into e power t by tau. So, and n naught is the initial injected excess electron density and tau is the carrier lifetime. Now, when you say about the recombination rate, you can say it will be you can take the integral of it. So, dn by dt, you can consider how much amount of the recombination is taken place. It will be given by n by tau, where and it is in negative. That is, it decays. Radioactive decay takes place. It will be reduced. So, it will be minus n by tau. Now, n is the electron density and tau is the carrier lifetime. So, it decays exponentially. So, as the recombination takes place, you can say the amount of energy will be released. So, the bulk recombination will be either in the radioactive recombination or it can also be in case of non-radioactive recombinations. So, all electron and hole recombination need not leave the basic photons. So, that only indicated by the non-radiative recombination. Radioactive recombination in the presence of a normal recombination of electrons and holes. But non-radioactive, it may not be there. So, it can emit your photons or it may not. It may be absorbed. So, the factors of recombination or the fraction of recombination will be considered in this particular case. So, normally the recombination rate will be 1 by tau. You can say in terms of your radiative recombination as tau r, and non-radiative recombination will be in terms of tau nr, where nr represents the non-radiative and recombination and your tau r indicates the radiative. With an external supplied current density J, we can say the rate equation of hole and electron will be changed to dn by dt in terms of t. So, J is considered is the current density supplied, that is your input whatever you are giving for your semiconductor. So, normally the forward biasing has been done for any photon emission. We take only the forward biasing of any PN junction diodes. but it should be of the higher concentration, not on the normal silicon. It can be a combined silicon, that is gallium arsenide or any such. So J by QD. Q will be the charge of the electron and D is the thickness of the recombination region. And N by tau already we discussed, it is the dN by dt. So we have with represent in case of the current density, we can say it will be equal to J by QD minus N by tau. In equilibrium conditions, we can say dN by dt will be 0. So the N will be equal to J tau by QD. It indicates how much amount of electron density is present in the presence of your current density or the J. And it also depends upon your temperature. And the internal quantum efficiency, when we consider, it also relates the ratio between the recombination, the radiative recombination towards the total recombination. So RR divided by RR plus RNR, and can also be expressed in terms of the carrier lifetime, and it is equal to tau of NR divided by tau R plus tau NR, where tau R will be the total recombination rate. So this internal quantum efficiency, normally it gives the total efficiency of the photon energy whatever observed in your semiconductor, that is LED or the laser. And the next comes your power, optical power, how much is being generated due to this in the LEDs or lasers. So it is related with the efficiency and the input current plus its photon energy. So it is a product of your internal efficiency, that is internal quantum efficiency, the current I by Q, which relates with the current density, whatever is being present for the input current, and the photon emitted HV. This can also be expressed in terms of your wavelength. So since we have your V, that is your V will be equal to C by lambda. So this also indicates the amount of power in terms of your wavelength. So at a particular wavelength, or I can say the designed optical signal at a particular wavelength will give this much amount of power. So your power internal is related with the injected current to the active region I, the charge available, and the photon energy H related with the wavelength. This constitutes your power. And the external quantum efficiency, it is also related with the number of photons emitted from the LED to the number of internally generated photons. It also applicable for the lasers too. Thank you.